Very good afternoon to one and all present here. Am I audible? Is my voice audible? Am I audible to all?
Yes, ma'am.
Thank you, sir. So, in today's session, we will take a case study where we are going to learn how to design a MEMS accelerometer. MEMS accelerometer with capacitive sensing because our standard process for fabrication is silicon based. So we can fabricate capacitive sensors, and we will understand how to design and simulate MEMS device with this fabrication process flow. And we will be taking or considering an application as accelerometer, right? So I'll be starting the session now. Um, I'm going to share the screen. Please let me know if the screen is visible to you all. Screen is visible to all?
Yes, ma'am, it is visible.
Yeah, thank you. So we will be understanding the design aspect and how to simulate the designed MEMS accelerometer using COMSOL multiphysics tool in this session. Before going into the design aspect, let's understand what is a MEMS accelerometer, right? So MEMS accelerometer is a device which is been microfabricated using MEMS technology, and the device dimension is in micron range, as we all know. But what is the speciality of this particular device is that it is capable of measuring the applied acceleration to it. Acceleration in terms of G, 1G, 2G. So depending on the design, we can model a device for sensing a particular acceleration. After sensing the acceleration, the device should be capable of converting this acceleration into equivalent electrical or electronic signals. Okay, so in our case, the electronic signal will be capacitance. So for applied acceleration, the accelerometer will experience a deflection in its body. The change in deflection will cause change in capacitance. So this is the principal operation of MEMS accelerometer. Why it is called as MEMS? Because the dimension of the device will be in micron range and they will be fabricated using microfabrication technology. So what are the key components for designing a MEMS accelerometer? As we all know, for mechanical modeling, three key aspects for modeling are mass, spring, and dampers, right? So damping, if we consider it to be zero, then the key component to model your accelerometer is mass and spring. So by fine tuning the mass and spring, we are actually going to design a MEMS accelerometer for a particular frequency or particular uh, application. So where can we use these MEMS accelerometers? Are every day we carry MEMS accelerometer with us. It is in our mobile phones, right? So when we try to tilt our mobile phones, the camera immediately pops up. That is because of the acceleration change that we are providing to the body of the accelerometer. So change in the acceleration is programmed in such a way that it triggers or invokes the camera application. So another application that we have understood in the very first session is the cruise control system, right? In our automobiles, if there is a change in acceleration which passes a threshold, then these accelerometer will actually deploy your airbag system, or even that is airbag deployment. In cruise control, to maintain a constant speed, again we are going with MEMS accelerometer to measure the speed of the car. So this, with this basic knowledge of what is MEMS accelerometer, let's understand this picture that has been displayed on the slide. So as I told, the key components for modeling your MEMS device is your mass and spring, considering damping to be almost near to zero. So you will have a proof mass. um the proof mass will be suspended through a spring, and modeling the spring and proof mass will actually allow you to model your uh, MEMS accelerometer. So now, so as I told, we will have a proof mass. It can be of rectangle or square shape. We will have a proof mass which will experience the applied acceleration. Okay, so proof mass can be square or in rectangular shape. Now, when I apply the acceleration to this proof mass, there is a movement in x direction, there is a movement in y direction, and there will be movement in z, and there will be also rotation in the z direction. Now, suppose if I want my proof mass to move in only one direction, right? If I want the proof mass to move in only one direction, then I have to restrict my proof mass to be moving in other directions. For example, I want my proof mass to move in y direction. I'm applying a acceleration in y direction, and I want my proof mass to only move in y direction instead of moving in x and rotating in z. For that, we have to model the spring. Okay, so if I want my proof mass to move only in y direction, then the proof mass should be suspended towards x direction. That means it should be restricted to move in x direction. So how do I restrict the movement of proof mass in x direction is, I will have a spring. It can be, there are many types of a spring. If I just have a simply supported beam, then it is called as parallel beam. Okay. This beam, one end is attached to the proof mass, another end is anchored. That means it is completely fixed. So if I uh, suspend all my four edges of proof mass in particular direction, that means I am going to restrict the movement of the proof mass in that particular direction. So this particular proof mass is restricted to move towards x, because freely suspended body is free to move in all three directions, and also it rotates in the z direction. So we, with this, what will happen? The sensitivity towards a particular direction will reduce. So it is required for us to model the device to move, have a deflection in a particular direction. So in order to deflect the diaphragm or the proof mass in a particular direction, we should restrict the movement of the proof mass in other directions. So the restriction is done by modeling your suspensions. So suspension modeling, if you are placing them in the x direction, how can I tell that suspension is in x direction? Is that the length of the proof mass is the proof the length of the spring is elongated towards the x direction. Now suppose if I have a proof mass, if I have a proof mass, and I want my proof mass to move in X direction, and I want to restrict the movement of proof mass in Y direction, then I will model my suspension in the Y direction. That means the spring will be elongated towards Y direction. It is restricting, or it is giving a stiffness towards Y direction compared to X direction. The stiffness will be more in Y direction. So if you want to model a device which moves only in X direction, then we have to model them by suspending them towards Y direction. So hope we have understood that the basic component for developing or designing a MEMS accelerometer is how carefully we are going to design a proof mass. Why modeling of proof mass is required is we all know that force is equal to mass into acceleration, right? So for experiencing a particular acceleration, modeling the mass is very important. The mass of the diaphragm is very important. Modeling them is very important, which decides the range of acceleration that can be sensed by the device. Okay, so modeling the proof mass is very important. And in order to suspend the device in a particular direction, the suspension systems are designed. In this particular session, we will concentrate on parallel beam suspension. What is parallel beam suspension? In all four side edges, there will be a parallel beam that are restricting the proof mass to move in a particular direction. So with this basic knowledge, we will try to understand the accelerometer that we are going to design. Before understanding the accelerometer, we will understand what are the different design considerations that we have to take care. So the first mechanical design consideration that is to be considered while designing your MEMS accelerometer is the range. For what range I have to develop the MEMS accelerometer? It is for 10G to 100G, or am I designing my accelerometer for 1G to 10G? So what is the range that is required for my device is more sensitive, right? For what range of acceleration my device should be more sensitive. Other acceleration, your device should be less sensitive. So deciding the range of acceleration is very important, and the range of acceleration is actually fine-tuned by modeling your proof mass and suspension system. Next, a mechanical design consideration is the sensitivity. So sensitivity again depends on, for applied acceleration, how much my proof mass is capable of moving, right? And the movement is again restricted by your suspension system, right? The more the stiffer, less the movement, less the sensitivity. So stiffness also should be fine tuned to provide a higher sensitivity. So again, modeling the proof mass and spring stiffness is very important in terms of sensitivity. And then natural frequency. In the previous sessions, we have seen the resonant frequency analysis, and we have understood that every device will have their own resonant frequency. What is resonant frequency is that at that particular frequency, the device will deflect maximum, right? So the natural frequency again uh, depends on the application. For example, airbag deployment. Suppose if the acceleration is maximum at a particular frequency, say 15 kilohertz or 20 kilohertz, then at 20 kilohertz, the airbag should be deployed. So to do that, the accelerometer that I have designed should provide maximum deflection around 20 kilohertz. So when there is a maximum deflection around 20 kilohertz, the electronic system will deploy the airbag, right? So designing your MEMS accelerometer for a particular resonant frequency is very important. And this particular resonant frequency fine tuning is also again done by carefully modeling your proof mass and suspension systems. So modeling proof mass and suspension system in our design of MEMS accelerometer or any other device is very important. So we have to understand a few governing equations which helps us to model them in a proper manner. Right? I have taken an example of a parallel beam accelerometer. A parallel beam accelerometer will have a proof mass which will experience the acceleration, and based on the acceleration, amount of acceleration, it will deflect. So this deflection, if it has to be in a particular direction, then the suspension system should be modeled. And the suspension system that I have chosen for this particular session is parallel beam suspension. Now, during when we go to the foundry, we all know that they will give us the footprint area in within which we can develop our device, right? In our case, mm, it is 9 mm into 9 mm. For just example, I have taken the footprint for MEMS accelerometer as 7 mm into 7 mm, and the thickness information is also given by the foundry itself. In this example, I have chosen the thickness to be 25 micrometer, and the material to design is silicon. Okay, so this is just for an example, but whenever you want to fabricate your device, then you have to follow the footprint area and the thickness material provided by the foundry. Okay, so you have 7 mm into 7 mm area within which you have to develop your MEMS accelerometer. And we know that for MEMS accelerometer, we need a proof mass and suspension system. So accordingly, you have to allocate the dimensions for your proof mass and suspension system, right? So again, the proof mass size and area depends on the three design parameters, that is the range, sensitivity, and natural frequency. Okay, for just for an example, I have chosen the proof mass shape to be square, and its size is 2.5 mm into 2.5 mm. The parallel beam suspension, the length of the parallel beam I have considered as 2 mm, width to be 25 micrometer, and the overall device thickness is 25 micrometer. One end of the spring is connected to the body, another end is fixed using the anchors. Okay, so this is the design of our MEMS accelerometer. Now, what are the governing equations? Okay, first we need to understand how to model the mass. Mass, we all know, mass is given by volume into density. Dear participants, just 2 minutes, I will be back. Okay, sorry for the interruption. So mass is given as volume into density. Okay, what is volume? Volume is the uh, volume of a particular shape. So we are considering a square. So it will be L square into T. into density, right? So in our case, we are considering the length of the proof mass to be 2.5 and the width of the proof mass to be 2.5. So it will be 2.5 mm, that is into 10 power minus 3 square. Thickness considered to be 25 micrometer, 25 into 10 power minus 6. And we all know that if we go to the console and select the material, we will understand the density value of our material silicon. From the console, the density is 2329. And if you calculate this particular value, kg per meter cube. So if you calculate this value, we will be getting the mass of around 3.64 into 10 power minus 7 kg. Okay, so after calculating the mass, we can calculate what is the equivalent force of a particular acceleration, because we know that force is equal to mass into acceleration. We know that we have to apply 1g acceleration, and we have calculated already based on the dimension of the proof mass what should be the mass of our diaphragm. So force can be calculated by mass into acceleration. 1g acceleration is converted again into meters per second. That is, it is 1g is equivalent to 9.81 meter per second square, but we will approximated it to be 10 meter per second square. So if you calculate the mass into acceleration, you will get the force that needs to be applied for the equivalent acceleration. So the force calculated is around 3.6 millinewton. That means this much amount of force is required to apply on the proof mass, which is equivalent to 1g acceleration. Okay. Now, we need to calculate the stiffness, spring constant. Okay. So in the cantilever beam session, we have understood that for a cantilever beam, stiffness is given as 3 EI by L cube, right? 3 EI by L cube. Now, that is a cantilever beam where the beam is fixed at one end and it is very free to move on the another end. But here, if you see, it is a simply supported beam. One end of the beam is supported by the anchors. Another end of the beam is supported by the proof mass. So for this type of beam, the stiffness K is given as 4 EI by L cube. Okay. The stiffness is given as 4 EI by L cube. And this particular stiffness that I am talking about is the stiffness provided in the direction of force applied. We are considering force to be applied in y direction. That is why we have suspended our proof mass in x direction. So stiffness along y direction will be very small, and that stiffness along y direction, that is the direction of applied force, is given as 4 EI by L cube. This is for simply supported beam. Now, what is the stiffness provided along the suspended direction? That is called as Kx. Okay, Kx is given as E is for Young's modulus, A is for cross-section area divided by L. Now, this Ky and Kx that I am talking about, sorry, very sorry, it is 12 EI by L cube. It's not 4 EI by L cube, it is 12 EI by L cube. Okay. The stiffness along the direction of movement is 12 EI by L cube. The stiffness to that is provided due to the restricted direction, it is EA by L. Now, this particular formula is applicable for one beam. Now, in our design, how many such beams we have? 4 beams, right? So, 4 beam each beam provides the stiffness in that particular direction. So when I multiply 12 EI by L cube into 4, then the overall stiffness provided KY overall will be 48 EI. E is the Young's modulus, I is the moment of inertia, and L cube is the length of the beam. And for X direction, where the movement is restricted, it will be 4 epsilon A by Young's modulus. It's not epsilon, it is Young's modulus E A by L. Okay. So that is what you can see in the slide. The y-axis stiffness, that is the direction in which the beam is moving, is given as 48 EI by L cube. Why it is 48? Because we are considering 4 such beams. All 4 beams are in parallel. Beams in parallel, where the stiffness gets added. So it is 4 EI by L cube. What is I? I is given as width into thickness cube by 12, d cube by 12. After I will tell you all how we calculated this stiffness. And stiffness along x direction, it is given as 4EA by L. Any doubt so far? Is the concept clear? So in my design, I have considered the length of the beam to be 2 mm, the width of the beam to be 25 micrometer, and the thickness of the beam to be 25 micrometer. So if I ask you all to find out what is the stiffness along the y direction ky, since the beam, the proof mass is moving along the direction y, you have to use the formula 48 EI by L cube. I is given as B d cube by 12. That means if this is my beam, if this is my parallel beam, then the thickness over the beam, it is considered to be D, and the width is considered to be B, right? So in our case, width and thicknesses are both are same. It is 25 micrometer and 25 micrometer. So I will be calculated as 25 micrometer into the thickness cube. Thickness is also 25 micrometer cube divided by 12. Okay. So if you calculate this value, you will get the I value. After you get I value, you have to substitute in the formula of 48. Young's modulus for silicon is 170 gigapascal. I we have calculated using the formula. And the L, that is the length of the beam, we have considered to be 2 mm. So it will be 2 into 10 power minus 3 power cube. After we calculate this, we get the stiffness towards y direction, which is 33.20 Newton per meter. Okay. Similarly, we have to calculate what is the stiffness provided by the beam in x direction. So in the x direction, the formula is 4EA by L. E is the Young's modulus. A is the area of cross section. That is again B into D, that is 25 micrometer into 25 micrometer, and L is the length of the beam. If I calculate that, you can see that the stiffness provided towards x direction is somewhere around 2 lakh Newton per meter. So if you consider the stiffness along y direction and stiffness along x direction, we can clearly notice that the stiffness of the proof mass towards x direction is very high compared to stiffness provided by the for the proof mass in y direction. So that means proof mass is very free to move in y direction, but it is almost very much restricted to move in x direction. Okay, so how do we calculate the sensitivity of the stiffness? It is through cross-axis sensitivity. Cross-axis sensitivity tells us that in which direction our proof mass can move very easily. Okay, it is usually given as kx by ky. So if you take the value of kx and divide it by ky, you get a cross-axis sensitivity. And for a good MEMS accelerometer to move in a particular direction, the cross-axis sensitivity should be above 5000. Okay, so that is how we design the suspension system. The displacement along y direction is given by force by spring constant, because we know that F is equal to K into delta, right? Where K is the stiffness provided by the proof mass. Now, which stiffness I should consider? The stiffness provided towards y direction, because I'm forcing my proof mass to move towards y direction. So I have to consider the stiffness along y direction, and D is the amount of displacement of proof mass. So if I know the force to be applied is known to us by the formula mass into acceleration. We will be knowing what is the stiffness provided by the proof mass in the y direction by calculating ky, which is 48 ei by l cube. Then we can know what is the amount of displacement my proof mass will go through. So it will be fy by ky. Okay, it will be fy by ky. So if by through design, we can actually understand what is the amount of displacement my proof mass will go through for a particular force applied. Force is equivalent to acceleration. And this is how we are going to design our MEMS accelerometer. If any doubt, you can ask me. Else we will proceed with the COMSOL. Is there any doubt?
Ma'am, how the A value is substituting, ma'am? For E into A.
Sorry, sir.
A value.
A is the cross-section area of your beam, the width into thickness.
Okay.
Yes. So with this very basic knowledge, we will just understand how to correlate our designed value with the simulation results. Okay. So to analyze the simulation of designed device, we will be using COMSOL tool. COMSOL takes some time to invoke because of multiple physics.
Excuse me, ma'am.
Yes, sir.
Ma'am, the thickness 25 micrometer that you
Yes.
have fixed, no, ma'am. That is not
Yes, sir.
given by
No,
foundry.
no, no, no. It is not foundry based. It is just for an example I've taken.
Okay, okay, okay.
We have to follow the thickness and the footprint area provided to us by the foundry.
Okay.
So we will be understanding how to design a MEMS accelerometer using COMSOL tool. So very first step is to double click on Model Wizard and select the space dimension, which is 3D for our MEMS devices. And then now here, while designing a MEMS accelerometer, it is actually two physics involved, right? One physics, which is allowing me to apply the equivalent force for the acceleration that I am going to design my proof mass. And another physics, after applying the acceleration, the proof mass deflects, right? Once it deflects, there should be change in capacitance. For change in capacitance, what I will do, I will be incorporating the Coombe drive fingers along Y direction. Can anyone tell me why along Y direction?
So
Why
less
I'm
stiffness
placing
is
my
why.
Coombe fingers along Y direction?
Y direction, less stiffness. The mass will
Yeah,
move to Y
very,
direction.
yeah, good. Y direction, the proof mass will actually display high sensitivity compared to any other direction because we have modeled our device to move towards Y direction with less stiffness. So the sensitivity will increase or it will be more in the Y direction. So I have to place my fingers directing towards Y direction. If I had to place my comb finger for this particular model, then it will be along X direction where the fingers are elongated towards X direction, right? So this is how we are modeling. So comb fingers will have one as fixed finger and another will be other opposite side will be movable, and one end of the one finger will be applied with high potential positive and another will be grounded or negative. So this is how we model our comb fingers. So to satisfy these two physics, one is solid mechanics physics, another is electrostatic physics. And now these two physics should communicate with each other, right? If I apply acceleration, proof mass displaces. The moment the proof mass displaces, the base capacitance should change. So the displacement should vary the base capacitance. So electrostatics and solid physics should be coupled. So this particular property we get in the physics called as electromechanics. Okay, so electromechanics combines both solid mechanics and electrostatic physics, allowing us to develop a coupled two physics coupled MEMS devices. So I'm going to add, I'll be going to structural mechanics. Under structural mechanics, I will be selecting electromechanics, physics, select electromechanics, and then click on add. Once you click on add, we can see that electromechanics is actually coupling two physics. One is solid mechanics, another is electrostatics. So once we add the physics, go to study. Initially, we will be adding stationary. As we proceed with the analysis, we will be choosing other studies. So I will be first initially selecting stationary study. Click on done. So once we have selected the all the required initial settings in our console tool, we can vary the length unit. For MEMS, the length unit is micrometer, right? And then we have to model our device, right? So for modeling, we have to go to geometry. Now, if we see our MEMS accelerometer, there are too many components integrated towards each other in a single plane. Okay. If it was just a square or rectangle shape, I could have directly chosen uh, block and given the dimension. But if this design is little bit complicated than the block, so instead of directly choosing the block, what I will do, I will right click on geometry, select work plane. So work plane gives me the feasibility. It acts like a plate, okay, where I can integrate multiple components together. Okay, so work plane allows you to have different shapes of models within a single plate. Okay, and all these, this plate is actually originated from 0 micrometer. That means they are starting from 0 micrometer. uh, so what did I do? I had gone to geometry, right click. I have chosen work plane. I had clicked on work plane. Once I click on work plane one will be uh, popping down the work geometry. And then under work plane, I have to go to plane geometry. So this is the work area which gives me the x-axis and y-axis control to design my device. Okay, so under plane geometry, right click. If you right click, you will be allowed to choose the shapes that is required to model your device. So since my proof mass is of a square shape, I will select the square, and then I will select square and then give the length. What is the length I have chosen? It is 2.5 mm into 2.5 mm. So I will be giving them in micrometer range, which is 2500 micrometer. Okay. After you give your dimension, click on build all. Your proof mass is built. After I build proof mass, what is required is the suspension system. The length of the suspension system, the length, if I'm talking about length, in COMSOL, it is equivalent to width, right? So in COMSOL, width gives you the length axis. So the length of my proof mass is 2 mm. So it is of what shape? It is of rectangle shape, right? So again, I will go to plane geometry, right click, select the shape as rectangle. The width is 2 mm, that is 2000 micrometer. The length is 25 micrometer. And then if you see here, I want my suspension to start from after the proof mass, right? Proof mass is ending at the origin point, uh, 2500 micrometer. So now I have to give the positioning from where the suspension should start. So the X positioning should be 2500, that is 2.5 mm. And then Y positioning should be 0, right? So click on build all. You see that your suspension of 2 mm into 25 micrometer is being built. Now the similar suspension is required in all four edges. In you either you can select rectangle again and again and give the dimension and positioning of your rectangle. Otherwise, if once the dimension is fixed and you want to replicate the same at different position, then what we can do, you can just right click on the shape that is required to replicate and select duplicate. Okay, you can duplicate it. The width and height of the suspension remains same, but what is only changes, it should be positioned towards on top, right? It should be positioned at top. So x-axis positioning will be same, but what will be y-axis positioning? It will be 2500 minus 25 micrometer, because always the COMSOL develops your models the device from top to down. Okay, so the positioning should be 2500 micrometer minus the um, height of your suspension. So if you click build all, you can see that you are creating a suspension on the top position of your um, device. Again, what you can do, you can duplicate rectangle one, because the same thing we require on the left hand side. Right click, duplicate. Now, X positioning should be changed because I am going to place them towards the left. So always COMSOL will develop models from left to right. Okay. So while developing below 0 axis, you have to go under minus positioning. So it will be minus the width. So minus 2000 width of your beam, right? And then again duplicate your rectangle 2. Instead of the Y positioning will be same, but the X positioning will be minus 2000, which is your minus the width of the um, beam. So this is how we model the suspension in all four direction. It is just playing with the positioning of your suspensions. Okay, how are you going to position your suspension such that it is going, one end is attached to the proof mass body and another end is fixed. Okay, this end is fixed. So with this we are able to design a proof mass and a suspension system. If it is required, you can also add a square which will act as an anchor. Otherwise, during simulation, anchoring can be avoided because directly we can fix the edge of the suspension system. Now, what is required is mechanical modeling is done. Now we should have a capacitive sensing components, which is our comb fingers. These comb fingers are elongated towards y direction. Again, comb fingers are of rectangle shape. So I will go back to plane geometry, right click, select rectangle. I will choose my width of the rectangle to be 100 micrometer, width of the rectangle to be 100 micrometer, and height of the rectangle to be 500 micrometer. Now, what will be the positioning of the proof mass? Comb drive. Uh, the axis, x-axis, it should start from this positioning. So x positioning is 0, whereas y positioning, it will grow from top to bottom. So it will be 2500 micrometer. Okay, so this is the movable comb fingers. Now we need a multiple array of movable comb fingers. So what we'll do, we will array this particular entity. How to array them? Go to plane geometry again, right click, go to transforms. You will have an option called array, select array. And then what you want to multiply, it is your comb finger, right? You require multiple movable comb fingers at a different fixed spacing. Okay, so select one particular comb finger. Um, Now you have to provide the positioning. Okay, so designing this particular positioning is very important. So suppose if I have a proof mass which is of 2.5 mm width, okay, I have a comb finger whose width is 100 micrometer and height is 500 micrometer. So I will be giving a gap of 100 micrometer. I will be giving a gap of 100 micrometer, and then after 100 micrometer, I will be having a stationary finger which is fixed. Okay, the stationary finger will be fixed, and again I will have a gap of 100 micrometer, and then there will be a replica of movable finger, and this will continue to be designed until the width of the proof mass is reached. So what is the total gap between the first movable finger and second movable finger? It is 100 micrometer plus 100 micrometer plus 100. So that is total 300 micrometer gap is been provided between the first movable finger and second movable finger, which is very true for between second movable and third. So we will be giving 100 micrometer. There will be a stationary comb finger. again 100 micrometer, and there will be a movable finger. So every movable fingers are placed 300 micrometer apart, right? So that information should be given to the console tool, and that is given by X and Y. So are they varying towards Y direction? No, they are only varying towards X direction. So what is the spacing? That is 300. So how many such elements I require in X direction? If I give 10, just random value 10, let's see what happens, right? It covers the even the suspension. So what is one extra is covering the suspension. Otherwise, the ninth comb finger is actually touching my proof mass, which is correct. So instead of 9 elements, I will give, instead of 10 elements, I will give 9 elements that is required as a movable comb finger. Click OK. So this is how we create arrays in console. Okay, one entity that should be replicated multiple times can be arrayed by this technique. The same thing if I want it at the bottom of my proof mass. So what I will do, I will go to rectangle 5, which is the first entity I modeled as a movable comb finger. I will duplicate it, duplicate. X positioning will be same. It should start from 0, whereas Y positioning, the width, the height of the comb finger is 500. So it should start from -500 and grow towards move towards X direction. So Y positioning will be -500. Click build all. We can see that the comb finger is duplicated towards the downside of my proof mass. Again, I have to have multiple movable fingers towards X direction. So what I will do, I will array them. Go to plane geometry, right click, transforms, array, select the entity that has to be multiplied, give the spacing, whether it can be spacing or Y spacing. In our case, it is spaced towards X direction, right? So the spacing between one entity and another entity is 300. How many such entities I require is 9. So we have to give these informations and click build all. So this is how we develop comb fingers to model our device. Now what is remaining for us to develop is the stationary comb fingers. Sorry. So again I will, again the stationary comb fingers, width and height is same, right? We need not to vary. Both movable and stationary comb fingers, width and height will be same. So I will duplicate rectangle 5. What is varying is the positioning, right? Now, instead of starting from x-axis 0, it should have a small spacing. What is the spacing now? It is 100 micrometer. Here in the base, we have selected the development as corner, right? So 100 micrometer plus it will start from the corner center, so 50 micrometers. So the total expositioning for creating your stationary comb finger will be 150 micrometer. Okay, it should start after 150 micrometer because the width of the first comb finger is 100 micrometer. Then I am giving 50 micrometer spacing, and then I am creating my proof mass, comb fingers, stationary comb fingers. And then it should not start from the, it should not touch the proof mass. It should be little above the proof mass. So I'm giving the gap to be 100 micrometer. Click build all and you will be modeling your stationary comb fingers. Again, after modeling one entity, you can multiply them using array. Go to plane geometry, right click, select transforms, array, select the entity that has to be multiplied, Now, what is the spacing between first stationary and second stationary? Again, it is 300 micrometer. How many such I require? Since movable entity were 9, now I require the fixed entity to be only 8 because one extra movable we require. Stationary entity will be in between the two movable entities. So if you click build all, all the arrayed comb fingers will appear. Now again, sir, please mute yourself. Sorry for that. Now again, if the stationary comb fingers has to be reflected towards downward of your proof mass, then what I have to do? I have to duplicate rectangle 7, duplicate it, and I have to give the.
How many tests left?
Sudhir sir, can you mute yourself? Okay, thank you, sir. So I have to duplicate rectangle 7, and then I have to give the Y position, X positioning. X positioning will be same because I'm duplicating the stationary comb finger, and Y positioning will be towards from negative to positive. The width of the height of the comb finger is 500. So it will start from minus 500, and the gap I am giving between proof mass and the fixed is 100 micrometer. So it will be minus 500 minus 100. So click on build all. Again, go to plane geometry, right click, transform, array, select the entity that has to be multiplied, give the spacing in X direction and the number of entity 8 and click on build all. So we have successfully designed or modeled our comb fingers, both movable and stationary. Now you can have a rectangle that is supporting your fixed comb fingers. So go to plane geometry, right click, rectangle. Width of the rectangle can be 2500 and height can be 1000 micrometer. So it is starting from the position y-axis 2600, right? Because it should start from here and then support your stationary comb fingers. Click on build all. Sorry, it is 2600 plus your height of your rectangle.
It's 3,100.
Yeah. Thank you. The same thing you can duplicate towards your towards the downward of your so it will be minus 1000 plus 110.
Minus 600. Minus 600.
Okay. So this is how we will be modeling our MEMS accelerometer. After we design the MEMS accelerometer, we know that proof mass, suspension, and the movable comb fingers are one entity, whereas the anchors and the stationary fingers are one entity. So we can, if I see now without union, if I select them, they are selecting in a different manner, like they are not a single entity. To make them a single entity, go to plane geometry, right click, booleans and partitions, select union, okay, and then select the entities that are one, okay, which are meant to be together. So I'm selecting the proof mass, I'm selecting the suspensions, and I'm selecting the comb fingers, movable comb fingers, which are attached to the proof mass. They are the single entities. Right? So after selecting them, I will untick the keep interior boundaries. It will be default ticked. We have to untick them and then click on build all. Okay. Now if we select, we can see that proof mass, suspension and movable comb fingers are single entity. Likewise, I'll go to geometry, plane geometry, right click, Booleans and partitions, union. Now I will select the anchors and the fixed comb fingers that are the second entity of our design. Both the side, anchors and fixed comb fingers. Untick the keep interior boundaries and click on build all. You can see that it will be a single quantity entity again. Sorry. So far, whatever I have modeled, it is the uh, uh, X value and the Y direction, length and width of the device is being designed, but the thickness information is nowhere given, right? So to provide the thickness information about the device, what we have to do, we have to go back to work plane 1, right click on work plane 1, and there is an option called extrude. Okay. Uh, Extrude will give you the option of entering the thickness information about the device. So under distance, you give the thickness that is for which the device is being designed. So in our case, it is 25 micrometer. So I will give the thickness of the device to be 25 micrometer. Click on build all. So if we can see that a 3D object of MEMS accelerometer is designed. So after we design our accelerometer, model our accelerometer, we have to add the material, okay, for which the device is being developed. So to do that, we will go to materials, right click, first option, add material from library. Towards our right, the library for the materials will pop up. Since it is silicon, we will go to MEMS, semiconductor, silicon, single crystal isotropic. Okay, we will choose single crystal isotropic, right click, add to component 1. So once I add to component 1, you can see that the model will turn into bluish color. That means the material is being added to the model or the design. Okay. After you add, now we have to provide the physics to the device. Okay. So as I told, so this is our designed parallel beam suspended MEMS accelerometer. Under mechanical physics, what we have to do, we have to fix the portion of our device and we have to apply equivalent force, right? Acceleration force that is equivalent to the acceleration. So all the edges of our suspension will be fixed because it is anchored. All our edges of our suspension will be fixed. It is anchored. And
സർ കുഞ്ഞെങ്ങനെയുണ്ട് അതെ ഞാൻ കാണുന്നുണ്ട് അല്ലേ
all the suspension edges will be fixed. And we know that in the comb drive finger, the anchored comb fingers also will be fixed. So the rectangle that is anchored, that also should be fixed. And then I am going to apply force or to the proof mass in Y direction. So if I go back to COMSOL multiphysics tool, Go to solid mechanics, which allows you to apply fixed constraint and apply the force. Right click on solid mechanics, choose the option of fixed constraint. Okay, and then you can tilt your or rotate your device. Use your zoom box to zoom the edge of your suspension, and you can select the face of your suspension, okay, which has to be fixed. So likewise, I will be selecting all four faces that need of the suspension that needs to be fixed, right? This is a zoom extent, okay? And then you can use your zoom box to zoom the area and select the face that needs to be fixed. I have fixed all the four edges of my suspension, and then the anchors that are supporting stationary comb fingers also needs to be fixed. So total there are 6 boundaries that is being fixed. After fixing the proof mass, after fixing the device, providing the fixed constraints, now I have to apply the force. So I will go to solid mechanics again, right click, choose boundary load. Okay, the force will be applied on the body, that is your proof mass. Select the entity and then come to the force load type, select total force as our load type, and then in which direction I have to apply the force. I have to apply the force in y direction. So what is the value for 1g acceleration? For 1g acceleration, the total force is 3.65 millinewton, right? So I have to apply 3.65 millinewton in y direction, 3.65 epsilon minus 3, right? Which is millinewton applied in the y direction. Okay. So I have fixed the, I have provided the fixed constraint and I have applied the load. Now, on the electrostatic physics, the fingers that is attached to proof mass will be grounded. Okay, I'll be grounding the fingers that is attached to the proof mass, and the fingers that are fixed, I will be applying the positive voltage to create electrostatic physics. So I will go to electrostatics, right click, choose ground. Okay, choose ground and select the proof mass. If you select the proof mass, automatically the movable comb fingers also will be selected. That means they are grounded. Again, go to electrostatics, right click, choose terminal, select the fixed comb fingers where that is to be positively charged. Okay, so change the terminal type from charge to voltage and provide the voltage for which you are modeling the device. So two physics that are communicating with each other. One is solid mechanics. Solid mechanics has two inputs, fixed constraint and boundary load. Electrostatic also has two inputs, ground and terminal. It is a multi-physics, that is both solid mechanics and electrostatics are coupled with each other. After providing the constraints, mesh your model. Once the model is meshed, we can compute our steady one, which is the stationary steady. So this is your total displacement of the proof mass. Okay, it considers all three directions. Okay, you can see there is a small displacement towards x, y, and z. Okay, if you want to know what is the exact value of movement in particular direction, then go to surface. Under displacement, there will be option called surface. In the surface, there will be option called replace expression. Click on it. Go to solid mechanics. You want to know about the displacement, so go to the option of displacement field. Now let's see whether my proof mass is actually modeled to move more in y direction compared to x and z, right? So if I check the displacement in x direction, I will double click on x field, plot. You can see that the proof mass is able to displace for the applied force in x direction, which is 20 micrometer. Okay. If I check the same thing in y direction, it is 60 micrometer, right? It is moving more in y direction compared to x. That means the sensitivity of the device is more towards y direction compared to x direction. And if the same thing, if I verify along z direction, it is just 2 micrometer, right? So x direction 20 micrometer, y direction 60 micrometer, and z direction it is 2 micrometer. So I have successfully designed a MEMS accelerometer which will have high sensitivity towards y direction. And how I am able to do it? It is by carefully modeling my suspension system. I am restricting the movement of the proof mass in x direction relatively to move freely in the y direction. Okay. And then if you want to know what is the amount of capacitance generated, you will have an option called electric potential in your results. Go to multi-slice. Okay, again go to replace expression. Now the physics is electrostatics for capacitance. Select that. The last option is terminals, and under terminal you will have something called as Maxwell capacitance. Double click on it and click on plot. So the capacitance value obtained is 4.45 into 10 power minus 43. Here the dielectric COMSOL default selects the dielectric as vacuum. But in reality, the dielectric of will be air. So we should have a air domain covered along with the device to get a better capacitance value. Now we have not covered our device with air domain, so it is giving the capacitance in considering the dielectric to be in vacuum. Okay, so it is, that's why the capacitance is very, very low, which is 4.45 into 10 power minus 43. So this is the mechanical and electrostatic analysis of our MEMS accelerometer. So theoretically, we are getting the displacement in y direction to be 100 micrometer, and through simulation, it is around 60 micrometer. Usually simulation and design value will have slight variation. So we have to bear with it. Okay. Yeah. And then frequency analysis can also be carried out. Frequency analysis, we know the resonant frequency in y direction, it is given as 1 by 2 pi root of ky by m. Okay. Before I simulate the eigenfrequency analysis, I request any one of the participants to kindly calculate this particular value, theoretical value. Okay. Ky value, I have calculated it to be, you can note it down. Ky value is 33.20, okay, Newton per meter, and the mass is 3.64 epsilon minus 7. Okay, so resonant frequency is given by 1 by 2 pi root of ky by m. Okay, please kindly calculate this and we will see whether it is matching with our simulation results. So to perform frequency analysis, we have to add a new study. So we will go to study, which is in the toolbar. We will select study, click on add study. Okay, click on add study. Towards the right, the list of studies will appear. Now, to analyze the resonant frequency, we have to choose eigen frequency study, right click, add study. And once you add the study towards your left, you will get the study 2, which is the eigen frequency. Just click on compute. Can anyone tell me what is the value that we are getting? It is 1 by 2 pi root of 33.20 divided by 3.67, 3.64 e power e minus 7. I wanted you all to calculate so that you understand how equations can be. To understand the equations in a better manner. Have anyone calculated the value? I guess you will get around 1500 hertz, right? 1500 hertz. So if we see the simulation result, the first eigen frequency is around 1300. So we are successful in satisfying the designed value and simulated value. The same thing can be plotted. The frequency response can be plotted. To plot frequency response, we have to choose another study, which is frequency domain. Select frequency domain, right click, add study. Once you add the study, study 3 will be invoked in your design model wizard. In frequency domain, give the range. Now we know that our first resonant frequency is around 1300. So I will be starting from 500 hertz in the step of 500 and I will reach till 3000. Okay. So add the step and compute.
Surya Prakash.
Console is taking some time to compute it. Meanwhile, any queries regarding today's session can be asked.
Ma'am, I have a question.
Please, sir.
Regarding the thickness specification, you told that the footprint and the thickness will be normally the definition from the foundry.
Yes, sir.
But that is in case we are working on a project of a third party, then as per their requirement or which foundry eventually they will approach. That will be the specification they will provide us.
There are two options with us. One, following the foundry standards. If we are following foundry standards, then we have to develop our device based on the foundry's uh, specifications. Another is customizing our device. When we go with customizing, then we can actually determine our own footprint area and thickness.
Okay, in that case, in the
Hmm.
customization, then eventually how the product will be taken to the foundry because they may have restriction, no?
That's what, sir. If we are going with customized fabrication process, then you have to decide which material, what should be the thickness of the
Okay.
material, and you should decide the area also, footprint area.
Okay, thank you.
But usually customization is very rare. We go with standard processes to satisfy the foundry requirements.
Okay, thank you.
Okay, sometimes what happens is the computation also depends on the RAM size your system has supported, right? If you have good RAM slots, then the computation will be very fast and you will get results. But in my case, I guess the iterations requires more memory to be computed, so I'm getting some error. But I have discussed how to find the frequency domain and plots in session 3 where cantilever beam was designed. We can follow the same. If any issue, we can you all can get back to me. I'm ready to help you all in this particular thing. Any other queries? In place of, sir, I just segregated the positioning value to make you understand. We can give it as a single value also. No issue, no problem.
Yeah, ma'am. One of the participant already answered. Thank you.
Yes, yes. So, yes, sir.
I have one query.
Yes,
And
sir.
what is the maximum G level the withstanding of the structure can be calculated, ma'am?
So maximum G level is dependent on the design. As I told, one of the mechanical design consideration is the range, right? So how the modeling of the proof mass and suspension decides the range of the acceleration that can be applied on it. So again, the design and modeling plays a crucial role in deciding the range of sensing the acceleration.
Okay.
So I guess with this, we will be ending the session for today. I'll be sharing the feedback form and quiz form in WhatsApp group. I request you all to fill both the feedback and quiz, attend the quiz. And at any time, if you have any doubt and if you are not able to undergo certain procedures, please contact me. I'm available for to help you all. And I guess Nikhila ma'am had mailed me regarding queries. I'll get back to her very soon. And thank you all. Thank you all for joining. Hope this session was good.
Thank you so much.
Thank you, ma'am.
Thank you.
Thank you, ma'am. Feedback
Thank you.
form is not visible, ma'am.
I'll be sharing it in the WhatsApp group, sir.
Okay, no problem.
This session link also video, if you share it, it'll be helpful to try
Yes,
this
sir.
out.
Yes, sir. Yes, I'll be sharing.
Ma'am, one request, ma'am.
Yeah.
Ma'am, is there any foundry data available as a technical notes, ma'am, to design the structures or any kind of applications?
Yes, sir. Yes, I'll share the same that also. And
Okay.
14th November, Dr. Sambudha Khan is going to address us about the standard process flow.
Okay. Okay.
I guess after that session, it'll be very clear to us
Okay.
what are
Okay.
the foundry processes.
Okay. Okay. Okay.
Yes.
Okay.
Hello, ma'am. Hello.
Yes, ma'am. Yes, ma'am.
Yeah, can you share the attendance link?
I will, ma'am. I will share.
Hmm. Hi, ma'am. Are you sharing it in the chat or in the WhatsApp group?